Hey, welcome to the last unit. We are on Unit 5 and we're going to be studying light. U5A1 is just going over some of the characteristics of light. I like to think that U5A1 sets you up for U5A2 and U5A2. That's the main one it sets you up for. We are not doing U5A3, so it's U5A1, U5A2, U5A4, and U5A5. Be sure to review transverse waves for this unit. Now it's going to mention longitudinal waves and torsional waves. We will not use those. Longitudinal waves are used in sound, and you did that in grade 11. Know the parts of a transverse wave, crest, trough, wavelength. Understand the relationship between frequency and period. Period is the amount of time in seconds it takes for one wave to pass a given point, where frequency is the number of waves that pass a point in 1 second. So remember the relationship. Frequency is 1 over big T, which is period, and period equals 1 over frequency. Also, know your universal wave equation. Just the derivation of that. Velocity is equal to displacement over time. What is displacement in light? It's wavelength. And what is time? It's a period. But scientists would rather use frequency, which is 1 over frequency. So if we rearrange this formula, we get velocity equals wavelength times frequency. Now, one thing you have to do as you get into activity 2, and this is probably the most important thing you can do right now, is to be able to visualize what a wave looks like from above. So if we look at a transverse wave from the side, it looks like this. The crests match up with the solid lines. The troughs match up with the dotted lines. Think of a wave at the beach. The wave is long, so there's a big wave front. So let's say the wave is moving in this direction. This is the front wave coming in. Then your next wave, then your next wave, then your next wave. Remember, when you look at it from above, the solid lines are going to be the crests and the dotted lines are going to be the troughs. Now, there are different ways we can describe waves and what they do. We can look at dispersion and reflection, diffraction and refraction. For whatever reason, in activity 1, they go over 3 of these characteristics. Actually, they only hit 2. I threw 1 in. So what you have to know about light is that light can reflect. So if it hits a surface and it comes back on the same side of that surface, that's reflection. What do I mean by coming back on the same side? It doesn't go through the surface when it reflects. An application there is mirrors. I am going to jump to number 3 and come back to 2 at the end. 2 is the most important one. If you remember what refraction is when light goes into a medium with a different optical density. So if it goes into a medium that has a higher optical density, like glass, it will refract or bend towards the normal. This angle here is going to be less than this angle here. So you might remember Snell's law, which you might hit in A5. And it shows the relationship between the optical density and that angle. Now, when the light leaves, it will go back in its original path. So the path of this light coming in should match up with this path here. So where does refraction occur in a real world? Well, glasses are a good example right there. So it's used to bend the light. So this is refraction. So in refraction, instead of saying on the same side of the surface, it passes through. Folks, remember, I'm giving an overall of what you should be studying in this content. I'm trying to give a quick description. And in this activity, all they're doing is going over background information you're going to need later on. Focus in on this one. This is the primary one right here, diffraction. And it's a property of light that has some real uses in technology. So what they have noticed is that here's your wavefront or your crest. As they come up to a small opening, they will bend and make this pattern like this. Now, they don't mention this person in this unit, but this is a guy named Ewan. He was a Dutch researcher, and he first noticed diffraction occurring. And what we can use is we can use the patterns from diffraction to calculate the wavelength of light. So in any system, you need to be able to do measurements to get a readout. So because diffraction occurs, we can find out the wavelength of the light. Now there's an apparatus called a spectrophotometer, which uses this. And for example, we can, in a crime scene, find a material. We can elevate that material to a very high temperature. It will give off light and we can identify what that material was. So that's just one use of this. So we can also use it in biology if we're studying, for example, chlorophyll, a pigment. And we can find the type of light or the colors of light that chlorophyll absorbs for energy purposes, or the type of light that it reflects. So because light has the ability to diffract or make these patterns as it goes through a small slit, we can do analysis on it. Get ready for this. This is going to be extremely important, and I'm going to do 2 separate videos for the next activity just so you can understand how diffraction works and why it's important. For light to diffract, this wavelength, or the distance between here and here, must be greater than the distance of the slit. So this distance must be greater than this distance, or diffraction will not occur. So we need very, very small openings for diffraction to occur.